Alright, this is the Dynamics project by Stefan Ha and Nathan Falk. This is problem 16-115. For this problem, we'll be using instant center analysis and acceleration kinematics. Here's the free body diagram, and we have a couple givens already. The angular velocity and angular acceleration of rod AB is given, and we have both of the rod lengths at 2 and 2.5 feet. Rod C is stuck on a collar, so there's only x direction velocities. So moving on to the instant center analysis, we find out the instant center by finding out what is perpendicular to the velocity of each end of B and C. C can only move in the x direction, so we draw a line up to find the instant center, and B moves at an angle of 45 degrees up to the left. So by using some trig, we find out our angles, and we name RBIC and RCIC. So moving on to our law of sines, we can find out RBIC and RCIC, and we figure out RBIC to be 1.7678 feet and RCIC to be 0.9151 feet. For our acceleration kinematics, we have the formula, which is equation. It's the acceleration of C equals acceleration of B plus acceleration of C with respect to B, and we have to remember that the two parts of the equation on the right side have normal and tangential components, and we need to account for these. So moving on to acceleration at B, we have the tangential acceleration equals alpha times r. Both of these are already givens, so it's just 3 times 2 equals 6, and this acceleration moves to the top left at an angle of 45 degrees. So when we sum up our equation of x and y values in the equation for relative acceleration, we can break it up. For the normal acceleration, that equals omega squared r, and both these are also given. It's 5 squared times 2, which equals 50 feet per second squared, and this is going at an angle 45 degrees down to the left. Moving on to AC with respect to B, here's another little schematic on the left to help you view how accelerations move. So the tangential acceleration is alpha r. Alpha is what we're trying to figure out. R is the length of the rod, which is 2.5, so that's what we have for tangential acceleration. And omega, however, we have to figure out a couple more things. We use V equals omega r. Omega is 5, r is 2, and so the velocity is 10 at this instant, because AB and BC are connected at point B, a pin joint. So we divide this by our instant center at B, 1.7678. We find out that to be 5.6567 radians per second. So we continue with our equation as normal acceleration equals omega squared r. So we square the angular velocity we just found, and we multiply that times 2.5, and that comes out to be nice and round to 80. And this is in a direction of 60 degrees going up to the right. Tangential, I forgot to say, it was going down to the right at 30 degrees. So now what we need to do is just sum up our accelerations and the x and y components. So here we have our equation summing up in the x on top and then on the y on the bottom. So the first two for right here, those are the AB, tangential and normal components, and the second two are the components of AC with respect to B. So we solve the y equation first. We figure out alpha to be 30.5 radians per second squared. So then we just plug that back into the first equation. AC equals -6 cosine 45 minus cosine 4550 plus 80 cosine 60 plus alpha 2.5 cosine 30. And we found out AC to be positive 66.5 feet per second squared. And that's the answer to problem 16, 115. And thanks a lot.